of what happened? Determination of system natural frequencies and mode shapes, mainly natural frequencies, using some of the techniques, popular methods. Some methods are approximate method, okay, that people are used to consider in the earlier ages, and even for to find out the fundamental frequency only, because the fundamental frequency is the quite important, right? The most important frequency, the first frequency. So we'll discuss about the approximate methods and also the trial and error methods, okay, right? So let us discuss about that, okay. So you don't have to be actually worried about too much about the formulation. Formulation means how the things are coming, how the formula is coming, or how the iterative scheme is coming, but you should know what basis it is coming, and then its implementation you have to know. That is the most important at this level, okay. For this chapter I am talking about, but obviously the theory and everything that we have discussed so far, that you should know what is basis behind that, and you should remember also. But for this thing, that is the determination of the natural frequency and mode shape, okay. In this case, so if you do not thoroughly or totally remember the formulation also, that is okay, but still you should understand, right, how it is coming, then you will be able to answer it if there is some typical question regarding that, okay. So first method that we are going to consider is Dunker-Lewis method, okay. So let us consider a 2 degrees of freedom system, simple 2 degrees of freedom system, okay, that can be extended to n degrees of freedom system also, okay. So this method will be used for finding out the approximate fundamental frequency, okay, right. So what is your eigenvalue problem? Eigenvalue problem is, so basically obviously you have to solve eigenvalue problem, right? Because the natural frequency and modes we are talking about. So k into u equals to omega square m into u. So we are assuming a 2 degrees of freedom system first for our simple calculation, and I am assuming that my mass matrix is diagonal, okay. Okay. So this can also be written in, written in the form k inverse, right, m u equals to 1 by omega square. Agree? Okay. The k is stiffness matrix, m is mass matrix, right? Okay. The k inverse is called the, defined as the, let's say, matrix A, and this is actually called the, when you learn your matrix structure analysis, this is called the flexibility matrix. K is stiffness matrix. It's called the flexibility matrix. Okay, fine. So now, so basically what is coming, A into M, okay, into U equals to 1 by omega square into U. So this is also an eigenvalue problem, right? From I have obtained this to this, okay. So for non-trivial solution of U, determinant of the coefficient matrix, that means determinant of A m minus 1 by omega square into obviously an identity matrix. Okay. Any issue with this thing? Is it okay? Fine. So let's say my I have inverted my K matrix and I got, so I'm just considering for a 2 by 2 system, okay. So determinant of A is, let's say, A11, A12, A21, A22, okay. And then M is my diagonal matrix M1, 0, 0, M2, omega square, identity 1, 0, 0, 1, determinant, correct? Okay, just for sake of example, I am taking 2 degrees of freedom because the calculation will be quite complicated. Okay, then we'll easily extend to the n degrees of freedom and then approximate for the fundamental frequency. That is the Dunker-Lewis method. Okay, so if you just do this, can you do this calculation and tell me what expression you are getting, what polynomial expression? Obviously, omega square, then omega 4, right? Yeah, so omega 1 by omega to the 4 will come. So tell me the polynomial. So it's since a 2 degrees of freedom system, so 2 natural frequency, right? So that will give in omega square 4 square. Then you can you tell me the complete the expression for this? Then obviously some coefficient into 1 by omega square, because it will be now a polynomial in 1 by omega square, right? Previously it was in polynomial in omega square, second order polynomial in omega square. Now it will be second order polynomial in 1 by omega square. So that is 1 by omega square whole square, some coefficient into this, then some constant term is equal to 0, plus or minus that sign will come. So please tell me, please fill up this circles. You should understood the procedure. You don't have to remember the whole procedure. I mean, for the purpose, you should remember the final thing, what final expression is, and what are the assumptions or what are the approximation it is going through. That's all. So till now, I hope everything is clear. There's nothing, just we have obtained from our standard eigenvalue problem, generalized eigenvalue problem. We have just assumed the K inverse is A, that is called the flexibility matrix, and we are dealing with a 2 degrees of freedom system with diagonal mass matrix. Okay. So please do the determinant and tell me what is the expression you are getting here. So 1 by omega square whole square, some coefficient into this plus something equal to 0.
So
Yes.
it's coming 1 by omega 4
That I have written 1 by omega square, then
minus
minus, okay. 1 minute.
A11
1 minute. Minus
so then in
A1,
bracket then in bracket
A1,
A11 M11
M1, M1,
M11 plus A22 M2.
M2.
So then plus A11 M11.
This is done, right? 1 by
Yes sir.
omega
Yes sir.
plus
A11 M1
A1 on M1.
A22 M2 multiplied both.
A1 on M1, A22.
M2
Okay, then
minus
minus
A12 M2
M2.
into A21 M1.
Okay, so I hope it is correct. You just check it. That is very straightforward. Okay. So let me write it proper manner. Okay. So this is 1 by omega square plus this thing equals to 0. Obviously, quadratic in 1 by omega square. Polynomial equation. So let us say it has obviously two roots, right? One is 1 by omega square and another will be 1 by omega square. Let's say it has two roots. Correct? So I can write very easily 1 by omega square by 1 by 1 minus square into, if these are the two roots. Agree?
Yes, sir.
All agree with me? Okay.
Yes.
Now just write it in the expanded form. So what I'll get 1 by omega square whole square. Now tell me what coefficient you are getting for 1 by omega square here, and what are the other terms. So other terms I can very easily see from here.
1 by omega 1 square plus 1 by omega 2 square.
1 by omega 1 square plus 1 by omega 2 square. Correct? Now comparing this with this coefficient of 1 by, so here the coefficient is matching 1 1, so this one is equals to this. Okay, fine. So that is 1 by omega 1 square plus 1 by omega 2 square equals to what? A11 M1 plus A22 M2. Agree? Anybody has doubt? Very simple. Okay, so similarly for n degrees of freedom system, it will be 1 by omega square, 1 by omega 2 square, 1 by omega 3 square, so on and so forth. 1 by omega n square equals to A11 M1, A22 M2, so on and so forth. ANN MN. Here, now Duncan is saying that you know that the fundamental frequency is the lowest frequency, then omega 2, omega 3, all other frequency are increasing order. Okay. So then He's saying that these quantities, these and higher quantities are lesser as compared to this. Correct? He's approximating it basically. This is an approximate calculation, not exact calculation. Okay. He's saying that these values are lower since this condition is there. Okay, because the omega 1 is the fundamental frequency, base frequency, and other frequency are the higher frequencies. So these values are much lower as compared to 1 by omega 1 square. Correct? So then he is approximating this expression as 1 by omega square is nearly equals to A11 M1 plus A22 M2, so on and so forth. Correct? This is nothing but the Dunker's form. To find out fundamental frequency in an approximate manner. Okay. So what you have to do? You have to just invert your stiffness matrix, then diagonal you take, multiply it with the masses, and then you will get the fundamental. Now quickly reply me. So using this approximation method, whatever you will get as omega 1, it will be lower or higher than the actual value.
Smaller than.
So all are agree with that? Okay. So basically it will underestimate, right? Okay. So let us just an example, take an example. 3 degrees of freedom system. Let's say 3 degrees of freedom system M1, M2, M3. Okay, so I am purposefully marking this M1, M2, M3 because for the next method it will be helpful to give the first mass as this one. Okay, then this is K1, K2, and K3. Let's say M1H. What is the numerical values I have taken? I forget. Just 1 minute, give me. Okay, 1, M2H2, M3H2. Just for simplicity, all kg, K1 equal to K2 equal to K3 equal to 1 Newton per meter. Tell me using Dunker's method quickly what are the approximate value of omega 1 in radian pass. Please, everybody, very simple, right? This is the formula, final formula. Anybody has doubt? You can ask. Anybody has any difficulty in understanding the formulation or what I am asking you to do? Anybody?
So 1 by root 5.
Tell me in the fraction.
Sir, I'm getting 1 by 3, sir.
1 by
3.
there is 0.333, right?
Yes, sir. 1 by 3, sir.
So all are getting the result, this result or not, or any difficulty. If you have any difficulty, please ask me, because these are very straightforward thing. Okay. Please see the formula again. 1 by omega square is approximately equal to a11 m1 plus a22 m2 plus this. So here it will be, for this problem, it will be a11 m1 plus a22 m2 plus a33 m3. m1 m2 m3 is given to you. Okay, you have to just find out a11 a22 a33. That is the diagonal terms of the flexibility matrix, which is nothing but the inverse of the stiffness matrix. So basically you have to formulate the stiffness matrix. That's all. Okay, should I move ahead in the next thing? Anybody has difficulty? Nobody. Very good. Okay. So now I'll just refer to the slides. Maybe it will be preferable. Okay, so obviously, as you mentioned, so the actual quantity, so in this omega 1, so I'll call it Dunkerelli method, right? So maybe say in superscript D, it will be obviously less than the actual omega 1 actual, right? So that you can check actually. You have already obtained mass and stiffness matrix. You can just find out the exact fundamental frequency, and you will find out that it will be, and whatever you obtain here using Dunkerelli's method is lower than that actual value. Okay. Okay. So here in the PPT I have given for 3 degrees of freedom system. Okay. Just you can go through it. It is a similar one. Okay. Now coming to the Holzer method. Okay. Very interesting. Okay. Long ago, Holzer has described this formula. Although it is initially used for torsional system, torsional shaft problem, but it can be conveniently used for like multi-story shear building, which can be idealized or modeled like this: M1, M2, M3, Mn, and this like this. So here displacements are x1, x2, x3, xn, and xn plus 1 also I am defining, which is the nothing but the motion of the base. In the present case, it is 0, right? Xn plus 1 is 0. Okay. Now just write the equation of motion, right? So first mass equation this, second mass equation this, third mass equation. It's very simple that you can write it. Here the free body diagram is also shown. Okay, please check this whether it's correct or not. Okay, or you can use the Lagrange or whatever method you have learned. Then you can write the equation of motion. Okay, and let us now assume my solution that x equals xi is equals to capital Xi cosine omega t in that form. Okay, get the solution. Okay. So if this is the solution, then I will substitute this. Xi means for I equal to obviously 1 to n, all the harmonic solution. So if I substitute this, let's say consider the first equation, that is this equation. Okay. So if I substitute that, I'll get this. Okay. Then for simplification, I'll get x2 in terms of, these are the amplitude, right? Capital X is the amplitude. Okay. So x2 is equals to x1 minus this. Anybody has any issue in this? Is a multi-degree of freedom system. I am writing the equation of motion using any of the approach, writing either free body diagram or Lagrange equation using energy approach. So these are my some equations. 6, 7, 8 is the equation of motion for the first mass, second mass, third mass, and so on and so forth. You can obtain. So I am concentrating on the first equation right now and assuming the solution in the form xi equals to capital Xi cos omega t, that is small x1 equal to capital X1 cosine omega t. Now if I substitute this in the first equation, I'll get this. The simplification, I'll get this. Equation number 1. Correct? Now I'll move to equation number 2. Substitute the assumed solution. That is equation number 7. If I go there, I'll get xt is equals to this. Okay? Then using equation 9. Now from here I will substitute x2 minus x1 equals to minus m1 omega square x1 by k1. Right? So this I will substitute in the next equation. Here x2 minus x1 I will substitute. Then you will get this. Okay. So if you repeat the procedure I mean, if you consider now the third equation, that is equation 8, and similarly, if you substitute here from x3 minus x2 from equation 10, then finally you get to the x4, and so on and so forth. So in general, I can write xn plus 1 equals to xn. Just follow this equation and see this equation. Xn plus 1 equals to xn minus omega square by k2. So here 2 it is 2, so it is n, it should be n, right? And summation of I equal to 1 to 2 here. m1 x1 plus m2 x2. That means summation of I equal to 1 to 2 mi xi. So here it is I equal to 1 to n mi xi. Okay. So this is the formula we are going to use to iteratively find out the mode shapes and the frequency of the system. Okay. That is the Holzer method. Okay. So that is iterative procedure. Okay. How to do that? Okay. So what is the value of xn plus 1? What is the value of xn plus 1? I mean, for 3 degrees of freedom system, if you have difficulty in understanding, please ask me. Let's say 3 degrees of freedom, m1, m2, m3, x1, x2, x3, this one is x4. Okay, so here n equals to 3. So what is xn plus 1? That means what is x4? Or capital X4. If x4 is 0, amplitude is also 0. What is x4? What is x4?
x3 minus omega square by k3.
No, that is fine. But x4 is what? Physically, x4 is what?
Ground motion.
That is 0, right? The ground is fixed here. We are not providing ground motion, right? We are doing the free vibration. We are to find out natural frequency and mode shape, right? The x4 is 0, right?
Yes, sir. If the condition is given.
Yeah, we are doing free vibration problem, right?
Yes,
Free vibration.
sir.
We have to find out the natural frequency and mode shape. So that is free vibration, right? So x4 is 0, right? Okay. So what we will do, we will start with x1. Starting with x1, right? x1 will some assume value we choose, okay? And finally we are going for x4, okay? So I'll just give through an example, okay? We'll discuss. I'll show you in an Excel sheet. So I have made an Excel sheet where you just give the input. So you also try to form an Excel sheet, or you can write a MATLAB code or whatever you feel preferable, okay? So I'll just simple way I'll show you Excel sheet, okay? So first you will just assume x1. Obviously you understood the fundamental frequency will be lower. I mean the first frequency will be lower, the second frequency will be a little bit more than that. So so x1 will consider, okay, and the omega square, that is the omega square will be assumed, okay. So then what will happen? X1 you can take as a 1, right, or any other value, so that will be reduced to the 0. So the procedure for Holzer method starts with the trial frequency, okay. So you have to choose a trial frequency, and you know, since the fundamental frequency is the lower, so choose some lower value, okay. So once you have, and assume that the mass of the displacement of the mass, amplitude of the displacement of the mass m1 is x1 equal to 1. Then you can find out x2. Once you obtain x2, you can find out x3. So on and so forth, you can finally go to xn plus 1. So for 3 degrees of freedom system, you have to find out x4 basically finally, right? Okay. Considering x1 equal to 1 and omega square, some assumed value. So if you find out that x4 equals to close to 0, then your assumption is correct. Okay? Right? But then how to see, how to, judge that whether that is a first mode, second mode or third mode, how to know that? That should we have to see from the mode shape. That is, whatever you are getting the values of, x1 you have chosen, x2, x3. So from those values, that is by seeing the shape, you have to conclude what is that mode. Okay. So I'm again repeating the discussion. Okay. So I hope everyone understood this expression, right? How it is coming. Okay. Now, I am going to use this expression to find out my natural frequencies in a trial and error manner. Okay, right? So first I am choosing, so I am starting from the top. Okay, so the first mass. So let us say x1, the amplitude of the first mass is unity. Okay, and some trial value of omega square. Some trial value of omega, that means omega square. Okay, I don't know whether there is a first mode, second one, I don't know. Okay, so I'll choose it. Then I'll put it here, find out what is x2. Then once I obtain, I'll get x3. Then I'll get x4. For this case, it is x4, right? And I'll see whether x4 is very close to 0, or if you got exactly 0, that is good, very good. Okay. So if it is exactly 0 or close to 0, then my assumption is okay. Okay. That is, that means this omega square that I have assumed representing some mode. Frequency of the sum mode. Not frequency. Omega square is the eigenvalues of the sum mode. Okay. That omega is representing the natural frequency. Okay. And how to conclude that this mode is first, second, or third by seeing the values of capital X1, capital X2, capital X3. Okay. Let us see an example, then it will be much more clear. Okay. So it is written here. So if xn plus 1 is nearly equals to 0, then the trial frequency is one of the natural frequency of the system, right? That I just told you, right? The trial frequency that you are choosing is one of the natural frequency of the system. Identify the mode number from the mode shape. Usually it is better to start with a very low value of trial omega to obtain the first frequency, right? So let me open the Excel sheet. Let me close it. Any difficulty in understanding? Hold on. Is the screen visible to you?
Yes, sir.
Yes.
You see. So the same problem, right? So all k are 1, right? So I have written here 1, mass is 1, 2, 2. Okay? Right. So you see, look at the table carefully. Okay. So serial number I have written 1, 2, 3. That means actually the it's representing this thing. Okay. The same problem we are handling M1, M2, M3, K1, K2, K3. It has X1, it has X2, and amplitude is X3. Okay. So first mass 1, right? Second mass 2, and third mass is 3. So mass is written here. Then 1 by Ki is written here. Okay. Because can you tell me what is the formula xn plus 1? Just tell me. I'll close that thing. Xn minus what?
So omega square.
Minus
Omega square.
by Kn into sigma mixi. So by Kn, sir.
Kn by?
Omega square by Kn
Omega square by Kn
into sigma of mixi.
mixi. Correct? So basically I am trying to find out this expression. You see here, this column. Can you see it? Okay. So first, why I have written here ui, very bad. It should be xi. To make it consistent, it should be capital Xi. Okay. You understood here ui is nothing but xi. Okay. So I have unfortunately I have written ui. Okay. So this should be xi. U is xi here. Okay. And here I can change it to x to ui. Okay. So u1. So I have chosen first, for the first mass I have chosen 1. Okay. Now systematically I am calculating. So MIUI. So I am trying to find out what is MIUI. So first, for the first case, MIUI is 1 into 1 is 1. Okay. Summation of MIUI, it's only 1, right? Because M1 into U1. So that is 1. This one, sorry, this one. Then I am calculating this. As a trial value, I have chosen omega square equal to 0.2. Okay. I have chosen. Let's see what will happen. Okay. So this is, I got this. Is the first line clear to all? First row? You see, this is just, for my convenience, I have do it in Excel sheet. You can program it in the MATLAB, that will be much better, okay. Or you can just, for simple problem and hand calculation through, you can check it, at least one case, okay. Right? So then go to the next mass. That means I want to find out basically X3, right? Sorry, X2, capital X2. Capital X2 I have to find out. So then this is my UI. How I am finding my UI? How it is 0.8?
Using that formula.
Huh?
Xn minus.
Yes, that is this 1 minus 0.2, right? Correct?
Yes.
Yes. I think it is confusing, so let me change this to x. Okay. So you got 0.8, right? So x2 minus x1, like that. Okay. So you are getting the, okay. So 0.8, right? Now MIXI will be 0.8 into 2, 1.6. The summation of MIXI, the previously M1 x1 and M2 x2, that is 1 plus 1.6, 2.6. Correct? 1 by Ki is already Ki. So if I do this, I'll get 0.5. How I am getting 0.28? That is 0.8 minus 0.52, right? Okay. Okay. X3 equals to X2 minus X3 equals to X2 minus this thing. Okay. X2 is this one, right? Minus 0.52 is 0.28. Okay. Then MIXI 0.28 into 2, 0.56. What is summation of MIXI? That means M1 epsilon plus M2 X2 plus M3 X3. So all three sum, right? Cumulative sum. Okay. Or from here you can visualize also. It's the 3.16. Okay. Is it correct? 2.6 plus 0.56 is 3.16. Correct. Okay. So then you can calculate this one. Okay. Then X4. X4 will be what? X4 will be X3 minus this thing, right? Okay. So X3 is 0.28 minus 0.63 is 0.350. That is X4. I have written the serial number 4, which doesn't have any mass. It is the base basically. This is the X4 actually. Right? Here it is the X4. So X4 has to be 0, right? Okay. But we have not got 0. So our assumption is very bad. Very bad assumption. Okay. So you have to properly choose it so that it is close to 0. Okay. So that means, so this omega square is not representing any eigenvalues of the system that is considered here. Now tell me, what value should I change from this 0.22? What should I do? Any suggestion?
Sir, if you increase, then that will be.
Let's say 0.25. It is increasing, boss. Minus 0.5625. So that means I have to reduce, right? So let's say 1.8. Still, you see, still in the minus sign. 0.16. Reducing. 0.14. Yes, it is coming close to 0. 0.13. Now doing a plus. So it is between 0.13 and 0.14, right? Correct? 0.13 is positive. We are getting X4 as positive. And if I do 0.14, then it is minus 0.03. So it should be between 0.13 and 0.14. Is it clear? Anybody has doubt? Is it clear? Just trial. I am trial and error. I am just checking. I am just checking it. Okay. So first he told that 0.25, so make it 0.25. So 0.25 where the I increased. So I just coming down, down, down. So I came to 0.14. It is minus 0.03. If I make further down, still it is not 0. So I am trying to make it 0.13, but it is going to the other side, right? Positive on the other side. So let us say 0.135. Yes. So what should I do? 0.134. It's almost 0. So let us stop it here. Okay. Minus 0.0002. So if this is my omega square, my omega 1 is written as 0.3661. What is using Dunkerley's method? What value of omega you got? 0.33, right?
0.8.
0.33. So and you can see here 0.33 is less than this. So it is underestimating. The Dunkerley's method is underestimating. That is proved. And omega 1, you can check it whether this is you are getting now whether this is omega 1 or not. Sorry, that I did not discuss, right? So this is one of the eigenvalue, that is sure. That is 0.134 is one of the, whether it is omega 1 square, omega 2 square, or omega 3 square, that we do not know. How to see? Let's see for this. What is the x that you are getting? You see all are positive, right? 1, 0.866, 0.5, right? Or 0.499, all are positive. So that is displacement is like, if I plot the displacement pattern, it will be something like that. And that is the first mode. Okay, so this is 1, this is some 0.8, and this is some 0.499, 0.86. Understood? If any one of this is negative, so it will be some different mode, right? So this is the first mode. So whatever eigen values you are getting, that is corresponding to the first mode. So I have written here omega 1 equal to 0.3661. You can check using the eigenvalue problem. You know k already, right? K and m is known to you. You just do the eigenvalue problem, k minus omega square m, take the determinant quickly and check whether you are getting the first frequency or fundamental frequency as this or not. You should get this because you see we are getting a almost close to 0. Okay. Everybody understood it or not? Very interesting, right? So you can just play around that, make an Excel sheet, take the different systems, third order system, I mean, you can always solve 3 by 3 system in your hand to check it. Okay. Right. So different parameters you choose and you make an Excel sheet or write a code and validate the results using Holzer method. Okay. Due to Henry Holzer. So similarly, you can do it for second mode and third. So is it clear to you? All of you are agree with me how we are finding the by trial and error procedure using Holzer method. So you see people invented different types of technique to find out the natural frequency, because those days the computers are not so fast or not so popular at that day, right? Okay. So how to find out for a big system? I like this type of shear building problem. So trial and error procedure. Okay. So let us check the second mode. Okay. So let me
Sir?
check this. Yes.
So like this is a linear system. For this, why we need to go for this method if we have another methods like
Another method means which method is available?
so like omega we find now omega 1 like we are finding here the natural frequency of the system. We can find by other methods also.
No, which method? You tell me which method. Please tell me.
So like that eigenvalue problems we are doing.
That is determinant of k minus omega square, right? That is what you
Yes.
are saying.
Yes.
Now I will give you a 10 by 10 matrix k and n. Please do a polynomial and try to solve it. Okay. Will it be easy or difficult?
Then it will be tough.
But this one, if you just make it in Excel sheet, it will be very clear, quickly. You can
Okay,
do
sir.
it. And also for 10 by 10 system, they'll find out only not all 10, first 2 or 3 they'll find out. Okay, and they'll get a idea about that. But nowadays the computation is so fast, numerically we'll just calculate it. If you give also 10,000 by 10,000 size also, within a minute it will solve it numerically. But not solving, obviously they will not form the software will not form a polynomial, right? Because that is inefficient. Numerical technique they will use, matrix method, and just find out the eigenvalues, eigenvector, everything. And just a click of a button. Okay. So we'll discuss one of the few method like matrix iteration method. So that is a kind of a method, but although that is also not used nowadays, that is a little bit more advanced than this simple method. So for similarly, you can do it for second mode, right? Okay. I don't know what has happened here. What is this? This is it. This minus this. So this should be this minus this. X4 is 0. So you see similarly this for second mode I have done. This is visible to you, right? Oh, before I have written here. Okay. Sorry. So just you can do the trial and error, and now you can see the mode shape 1, 0, and minus 1, right? So this is representing the second mode. Okay, that means first one is, so the plot is like that, 1, someone is 0, and another is in here like that minus 1. So this is minus 1, this is 1, and here it is simply 0. So this is the second mode representing, and the frequency is 1. Okay, so please quickly check what is the exact result for this. Okay. By doing k minus omega square n. Eigenvalue problem 3 by 3 system. Use your calculator and do it. This is for the third mode. Again, I have obtained u4 equals to, with these assumptions, okay, I got u4 equals to minus 0.003. And in this case, look at this. Why it is third mode? Because this one. This is the first mass here. So this is 1. Then this is minus. This is plus. Okay. This. 2 nodes, right? Crossing. So that means the third node. Clear?
Yes, sir.
So please quickly do the calculation. What is the exact natural frequencies omega 1, omega 2, and omega 3 for the system I have given to you? So this is verified that the Dunker-Lewis method we have got 0.33 and it is underestimating, right? We have got 0.366, which will be most probably the close to the exact natural frequency, fundamental frequency, but we have obtained the fundamental frequency using time release method as 0.33. So it is underestimating, right? Because those terms it is neglected. Higher modes it is neglected.
Sir, I'm getting 0.366.
So 0.36. You see the Holzer method, okay, without solving the polynomial characteristic equation or frequency equation, iteratively you are getting 0.366. What is the second mode frequency?
So 1.
1.
Yes, sir.
This is the exactly one because you see U4 is 0, exactly coming 0. Third mode, there might be some difference.
1.36.
See?
6.
This is also correct. Almost not equal to. Okay. So try to solve similar type of problem. Okay, make your own convenient Excel sheet or coding, whatever you prefer. Okay, this is my way of writing the. I mean doing the Excel work. Okay, so you can do it in a much better way or whatever you feel comfortable, and just play around it. And for at least for one problem, first solve. First do not solve obviously the exact values. Okay, then you will be giving the values close to that value, right? So first do the trial and error. Okay, and then first use the Holzer method to find out the frequencies omega 1, omega 2, omega 3. Then in an exact manner solve it and check. Okay, and also use the Dunker release formula. One thing you can do, you can first apply the Dunker release formula to get the approximate idea about the fundamental frequency. Okay, so let's say you got 0.5 as the fundamental frequency. So you are aware that it will be around either 0.55 or 0.6 like that, actual one. Okay, so from that you will get the idea and you can start the iteration. Okay. Okay, so I'll stop it here today. Okay, so we have discussed two methods, Dunker-Lewis method and the Holzer method. There are some other few methods is there that we will discuss. One of the important and concept-wise you should know, that is the Rayleigh method. Okay, so that we will discuss. Okay, and it has some very interesting properties that Rayleigh method has. Okay, so the Rayleigh method we will discuss, then matrix iteration method, and most probably the Jacobi's iteration. Maybe Jacobi you might have learned if you have done your mathematics courses on numerical method. Okay, Jacobi's method is there. Okay, but anyway, Rayleigh method we should discuss. Okay, and we will discuss in the next week, right? Okay, fine. So today I'll stop it here. If anybody has any doubt, since the time is there, I'll be here for 5 minutes, so you can ask me. Otherwise, the class is actually over, so you can leave if you wish.
Excuse me, sir.
Yes.
Sir, can you please extend the deadline of one more day?
Extend the
assignment deadline for just one more day.
No, I know that is not possible because it is too much time I have given. The problems are very simple. Okay, just to find out eigenvalue, eigenvector, right, and verify that it is the same problem I have discussed in class. And even if I not discuss also, since you have understood, just go through any books, just see the example how they have solved it, and you can, even if you just sit for 2 hours, you can solve it. 2 hours. Let's see, you have not started yet. If you today only start, you sit from 8 to 10 at the night I am saying. Okay, you will be able to finish it. Okay.
Sir, sir, at least like today till 12 p.m. can you keep the deadline, sir? Now it's at 8:30.
Today 12 p.m. Okay, fine. Today 12 p.m. Okay.
Sir, I mean night 11:59.
Huh?
Sir, night, sir, midnight. Today midnight.
Today 12. Yeah. Instead of 8:30, you are asking to 12, right? 3.5 hours more, right?
Yes, yes.
Yeah. Fine. Okay. But that actually lead to the dangerous thing and unfortunate thing, unacceptable thing of copying from each other. Okay. That is the thing. But since you are asking, okay, so this time I am extending the time from 8:30 to 12. But I expect everybody to do by yourself, because you see these are not very difficult problem, right? Whatever I have given, and these are repeatedly I discuss in class. and you can go through, books are available to you, right? You just go through any example problem, how they are finding the natural frequencies, mode say, verifying the orthogonality condition. Those are the basic problems, right? Then you'll be easily able to do that. Yeah. Okay. So if anybody has any doubt, they can ask me.